step response. So we have seen the general equation. So if you solve that, or if you replace that differentials by variables, we get the characteristic equation. So d square y by dt square is replaced by lambda square plus 2 zeta by omega and lambda plus 1 equal to 0. So this is the characteristic equation. Now the solution to the differential equation depends on the values of the characteristic equation, values of lambda in the characteristic equation. The roots are minus zeta omega n plus or minus omega n into root of zeta square minus 1. So this is, I hope you are familiar, studied this second order system in many places. In mathematics, you have studied in details how to solve this and all, which I have forgotten perhaps. Okay, so these are the roots. Now, depending on these values, the solutions will differ. So what are the different solutions? So it depends of course on this. So the homogeneous solution depends on the value of zeta. So when zeta is between 0 and 1, we have what is called the underdamped system. Okay. So here the solution is the homogeneous solution is c e raised to minus zeta omega n t into sine of omega n into root of 1 minus zeta square t plus some theta. So this is the solution. So we can see that this is of the form of e raised to minus zeta omega n t. Okay, that is exponentially decaying. Okay, when t equal to 0, e raised to 0 is 1, so this is 1. And when t is infinity, e raised to minus infinity is 0. So this is the transient part. So this part is 1 when t equal to 0. When t equal to infinity, this part becomes, it vanishes. So that is the homogeneous solution. So for the critically damped system, zeta equal to 1, the homogeneous solution is C1 e raised to lambda 1 t plus C2 t e raised to lambda 2 t. So here we have, this is exponentially increasing, this is also exponentially increasing. Okay, here, of course, one part was exponentially decaying, but there was one part which was sinusoidal. Okay, that means whatever be the input, we are not actually decided what should be the input. It can be any input. This is the homogeneous solution. For the transient, there will always be some sinusoidal signal. Okay, so this is actually before step input. We have not used the step input part here. So whatever be the input, if the system is underdamped, there will be a sinusoidal oscillation. If it is critical, there is no sinusoidal part in the transient response. And overdamped system, when zeta greater than 1, we get the homogeneous solution as C1 e raised to lambda 1 t plus C2 e raised to lambda 2 t. Okay, so these two are the solutions to the characteristic equation, lambda 1 and lambda 2. Okay, so when it is overdamped, when zeta is overdamped, we have two exponentially decaying exponentially increasing systems, and here it is t into x e raised to lambda t. Okay, so that is the transient response. So this is a summary of the mathematical equation we have seen earlier. For underdamped system, transient responses oscillate. So whatever be the input signal, the response is an oscillation. If it is overdamped, there is no oscillation, but it exponentially reaches the final value slowly after a long time. Critical damping is similar to, there is no oscillation, but it reaches the final value the fastest. Okay, so this is about the transient response. Now, the other part, the step input. Okay, so we have a spring mass system, which is in equilibrium position, and suddenly you disturb it. What will happen? Of course, it depends on the damping ratio. Okay, pure spring mass system, there is no damping. Okay, that is an underdamped system. So you simply disturb the system, there will be oscillations. The mass will just keep going up and down. So this is our aim, to determine the general behavior and speed at which the system will respond to a change in input. So when the input changes, so you are suddenly applying a step input, and next, of course, we are suddenly applying a sinusoidal input, what will be the response of the system? So what will be the system show, and how fast will it be able to respond? So that is our aim. So the solution for the case of a step input is, okay, we are not going to the mathematics of it, we will just use the final solution. So when zeta is between 0 and 1, the solution yt is, the complete solution is Ka minus Ka into e raised to minus zeta omega and t. So A is the amplitude of the unit step function. Okay, you are giving a sudden input, the amplitude A, the step is A. Okay, unit step function is has amplitude 1. So you multiply that by A to get the whatever step function you are giving to the instrument. So that into Ka is the ideal step response. Okay, when you give a step input of A, the instrument should show Ka. So that is a ideal step response. So Ka minus Ka into e raised to minus zeta omega and t into zeta by root of 1 minus zeta square. So zeta is the damping ratio by root of 1 minus zeta square, and zeta is less than 1. Okay, so that is why here it is 1 minus zeta square. Zeta by root of 1 minus square into sine of omega n into root of 1 minus zeta square into t, plus cos of omega n into root of 1 minus zeta square into t. So sine something plus cos something, but sine is again multiplied by something. So, and it is multiplied by e raised to minus something. So this is the, so you can substitute various values. So we are interested in what will be this. So all these are properties of the system. Okay, K, A is the input of the this step input. What is the height of the step? Zeta is the damping ratio. Omega is the natural frequency of the instrument. T is the time. So we would like to know how Yt changes with respect to T. Okay, as T increases, what happens to the output of the instrument? So this is also a property of the system. It does not change with the instrument. Omega does not change. So only T is the variable. So you can substitute various values of T. You can try in Excel, enter this equation, and for various value of T, what will be the Yt? Okay, so that, okay, if you do that, it will be useful to solve problems also. Okay, so when zeta equal to 1, what will happen? Okay, that is a not this the solution. Okay, so that again we have to go back to the mathematics. So yt is ka minus ka into 1 plus omega nt into e raised to minus omega nt. Okay, so omega and t is always occurring together. So final response will be Ka, and because t as becomes infinity, it becomes 0. So for this case, and then when zeta is greater than 1, the solution is yt equal to Ka minus Ka into e raised to minus zeta omega t into. So now we have two terms, zeta by root of zeta square minus 1. So now zeta is greater than 1. So that is why it is square root of zeta square minus 1. So into sine hyperbolic of omega n into root of zeta square minus 1 into t plus cos hyperbolic of omega n into root of zeta square minus 1 into t. So this is the complete solution of, or what will be the response of y. That is how the instrument, what reading the instrument will show. That is your y. The input is a step input of a step change of amplitude A. Okay, then this will be the output. So these are both hyperbolic functions, sine hyperbolic plus cos hyperbolic. So this is, okay, there is no oscillation. Okay, it is going slowly to the final value. So we can plot the graphs of these equations. Okay, so no need to memorize for the exam, don't learn by heart. If required, this equation will be given. Okay, but be familiar with the terms. Okay, what is all this or how to obtain them. Okay, so this is the solution with the graph. So when zeta is between 0 and 1, yt is Ka minus Ka into e raised to minus zeta omega and t into, okay, this is what just now we are seeing. So this is the solution. So if you plot this graph for, since omega n occurs here, omega n into t, we make that a variable to generalize it. Then, so when t equal to 0, the output will be 0. So you are giving a step input of, so this y-axis is yt by Ka. So Ka has been taken down. So 1 minus e raised to minus. So at t equal to, ideally it should be Ka. That is yt by Ka will be 1. So ideally it should reach here. Okay, so this is what it should show, but actually it will show different values depending on the value of zeta. So when zeta equal to 0, that is, there is no damping at all. So the signal will show. So when t equal to 0, it is sine omega n. Zeta is 0, so this will be sine omega n t plus cos omega n t. Okay, so two sines. So it will be sinusoidal. Okay, when zeta is 0, the output is completely sinusoidal. So that's very interesting. You are giving only a sudden step input, but there will be oscillation. So we have created vibration. So you might have noticed in your manometer and all, sometimes when you give a sudden increase, the manometer will start oscillating. Okay. So if there is no damping, it will keep on oscillating forever. It will never reach the final value. But the mean value, if you take the average, it will be equal to 1. That is an ideal value. Now, if zeta is more, say 0.25, then there will be damping. So you can see the green curve. So it will increase at first, then decrease, like that, oscillate. Okay? But of course, after a few values of omega and t, say omega and t greater than 12, it is almost equal to 1. So it has reached the final value. And if more damping, say omega and t equal to zeta equal to 0.5, By the time omega t is somewhere here 5, it is almost close to 1. Okay, it is just very small oscillations are there. Practically, you can't see. So it increases slightly and then comes down. It increases beyond 1 and then comes down to 1. So this is the response of a second order instrument with damping ratio less than 1. With more and more damping, of course, this reaches 1 and the oscillations are even smaller. So you can see 0.5 is good enough. So generally for instruments, we choose a damping ratio of 0.7. Then practically there will be very small oscillations. So for zeta equal to 1, damping ratio equal to 1, yt by Ka. So here in this equation, it is just exponentially decaying this part. Final value is Ka. Ka is 1. Yt by Ka will be 1. So it increases exponentially. So just like your first order system, okay, it just increases exponentially and reaches the final value. So that is for critical damping. And then if damping ratio is greater than 1, so we have this hyperbolic functions. Anyway, this is the only place where hyperbolic functions are appearing in Tech, I think, mechanical. So here, okay, the graph of this function is shown here. So with damping ratio 1.5, we have this pink curve. It is not exponential, it is slower than exponential. With damping ratio increasing, it becomes very slow. Damping ratio 3 takes a long time, does not reach the final value after even, say, 15, omega and 10 equal to 15, is still not reached 1. So this part is not very useful. Okay, so we want our measuring instrument to show the correct reading at the earliest. Okay, so but a high damping means, so sometimes you might have seen speedometers and all in buses. Of course, now most of them have become digital, but the old speedometers, if you see neutral type, you can see some, it will keep on increasing as if, okay, it's not reached the final value. Okay, so this is step input. Okay, the response of an overdamped system to a step input. Okay, it increases rate. So you are given a step, but it does not reach the step immediately, but reaches the final value after a long time. Okay, so remember these graphs. So you can get questions to plot one of these graphs for a particular damping ratio. So remember the variables omega and t, and left side is yt by Ka. Okay, so you don't have to learn by heart this equation. Of course, one problem is where you have to use this equation. So you have to learn to substitute the values and find out, okay, y for different values of t. Okay, or we have to solve for, okay, that is a time for a particular value of y. So you want the response to reach a certain value. After how much time will you get that value? Okay, so damping ratio. So the best damping ratio for measuring instruments is generally mentioned as 0.7 because it offers a good compromise between rise time and settling time. Okay, these two times are we will define later on the next slide. So rise time is the time required to reach the final value, and settling time is the time required for oscillations to stop. So most dynamic response measurement systems are designed such that damping ratio is between 0.6 and 0.8. So that's the tolerance of plus minus 0.1. So we can't make it exactly 0.7 sometimes because temperature of the fluid, etc., will change. The friction forces, the damping depends on friction. Okay, so it is a little unpredictable. So that's why we aim for 0.7 and allow a variation of 0.6 to 0.8. Okay. Next we come to ringing frequency. So omega d. So ringing, what is ringing? So we are giving a sudden step change to the instrument. So like a bell, you are giving a hit to the bell. So what will happen? The bell will ring. With what frequency? That is your ringing frequency, omega d. Omega n is the natural frequency, but because of damping, it will not ring with that same frequency, it will be slightly changed. That is, for underdamped systems, the transient response is oscillatory about the steady value and occurs with the period Td equal to 2 pi by omega t. Okay, we want to find out this, so that's why we use this omega t. And omega t is equal to omega n into root of 1 minus zeta square. Okay, so this is for underdamped systems. Okay, so that is zeta should be less than 1. So when it is close to 0, this will be large. So it will be omega n into root of 1 minus something. So it will be reduced. So omega d will be slightly smaller than omega n. So because of that, the time period will increase. Okay, so this is the free oscillation frequency of a system displaced from its equilibrium. Okay. You disturb a system, with what frequency will the system oscillate? So now we come to the definition of rise time. So how fast will the instrument respond? So that is quantified using the term rise time. The time required for a second order system to first achieve a value within 90% of the step response, Ka minus Y0. Step response is Ka minus Y0. So Y0 is the initial value where the instrument is now. So usually it will be 0, but it may be at some place. And Ka is the final value. So Ka minus Y0 is the step response. So 90% of this K is the final value of shown by the instrument. So 90% of that value, when will it reach? That time, that is the rise time. And the other parameter of an instrument is settling time. So we have seen that an undamped system, there will be oscillations. But after a short period of time, it becomes, especially if there is more damping, so around 0.7 for measuring instruments, it will become very small. The vibrations will be very small. So when will it become lower than plus or minus 10% of the step response? So that time, the time required for the measurement system's oscillations to settle within plus or minus 10% of the step response, Ka minus Y0, is defined as settling time. Of course, this 10%, some people always write here the value. So rise time or 90% rise time, 95% rise time, etc. people write. In some books, you commented that there. Okay, if nothing is mentioned, you assume 90% for rise time and 10% for settling time. Okay, in our course, you can assume that. Okay, to be more precise, of course, if you say settling time, 10% settling time, that means it should settle within plus or minus 10% of the step response. So now we'll try to estimate this from the graph of Y, the response of the instrument. So the problem, find the rise time, settling time, and damp natural frequency of the second order system subject, whose response to a step input is shown in the next slide. So you are giving a step input from 1 to 2. So, okay, this is the response. Finally, it should reach 2. Okay. So initially it is at 1, finally it is reaching 2. So it is an underdamped system. So it goes up, rises, goes above, comes down, and then oscillates. Okay. So Y0 is 1, K is 2. So Ka minus Y naught is 2 minus 1, 1. So 90% of that is 1.9. So first time it reaches 1.9, that is your 90% rise time. And then goes up, reduces, oscillations happen, and from what time onwards it is within plus or minus 10%. So final value is 2, so plus or minus 10% is 1.9 to 2.1. So draw two lines parallel to x-axis. So here it is not crossing below 1.9. So we can take this as the settling time, 10%, plus or minus 10% settling time. Suppose it had crossed here slightly below, then settling time would be after coming back here. This would have been the settling time. Okay. So you have to be careful in evaluating settling time. Okay. So, okay, so from the graph, okay, rise time is 0.0038 seconds or 3.8 milliseconds, and settling time is 0.009 seconds or 9 milliseconds. So the damped natural frequency is 2 pi by Td. So Td is the oscillations of the system, the time period of the oscillations of the system. So from the graph, we can determine this as 0.013 seconds. So 2 pi by Td is 483.3 radians per second. Okay. Okay, so that is, okay, this is an additional problem. I think this problem is there in the observer quiz. Okay. So this you have to do with some numerical solution. An automobile weighing 2000 kg moves down by 40 mm when loaded with 1000 kg. So the weight of the system is only 2000 kg. So these two values are given to us to estimate the spring constant. Okay. So spring constant K is force by deflection, 1000 by 40. So 1000 kg. So you have to multiply by G to get force, right? Deflection will be spring constant. Estimate the rise time of the system if the damping ratio is 0.6. So damping ratio is given. So we can solve that equation and determine the rise time. So rise time means Yt by Ka should be 0.9. So for 0.9 Yt by Ka, what should be T? So that you have to solve numerically. So we can also use from the graph. We can have enlarge that graph and then obtain the value of T. So M is 2000 kg. Okay, question is a little vague whether 1000 should be included over here. But I think this is taken from the textbook and I will not change it, the wordings. So mass is 2000 kg. Now omega n is root of K by M. K we have to determine from the other data, and root of K by M. Zeta is 0.6 is given. So damped natural frequency, omega n into root of 1 minus zeta square. Zeta by root of 1 minus zeta square is 0.75. And then we have to find out y by Ka. So you saw for a particular t, sin omega dt, cos omega dt, zeta into sin of omega n t by root of 1 minus zeta square t, e raised to minus zeta omega n t, zeta into sin of omega. So all these you have to calculate and finally you get Ya. So now you have to try various values of t and till you get the required value of y by Ka as 0.9. Well, Excel, you can change t using the function, given libraries. Or if you're using calculator, you can use solve. I think I have put a note in the edge server. So only the solve function, or you have to do trial and error, you have to change the values. You have to start with the initial value close to this, the correct value, then it will not be, there will not be a problem. If you choose so far away, because it is oscillating, so you may get intersections where the point is much far away also. So that is the point you have to be careful about, because there are oscillations, and which is the first point. So anywhere where it meets the 90% line can be taken as the solution, which is simply solved it numerically, but we are interested in the first point. Okay, so that you have to be careful when you do this problem. So this problem, I think, okay, I'll enable this, and we need one more class to complete this. The second order system with the sinusoidal input. Okay, of course, video is there in YouTube. Okay, if you can, since even otherwise attendances, so there's no point. If we can have a discussion section later if you have any doubts. Okay, so please see the video on your own, and this weekend you can attempt the problems for both the cases. Okay, so there is one quiz which is multiple choice quiz, and then problems on second order system step input, second order system sinusoidal or frequency response. Okay, two sets are there. So this is another way this final solution is written for M is in some books you can see. So theta is this, the delay, lag. Okay, this is another problem. The mercury manometer is a mercury column of length 0.6 meter. The acceleration due to gravity is 9.8 meter per second square. A sudden pressure was applied to the manometer, resulting in deflection of 50 mm after a long time. So this is the final value. The damping ratio is 0.6, determine the 90% rise time. So very similar. So you have to, of course, you have to find the natural frequency of the manometer, which you have learned in the previous class. Okay, how to calculate the natural frequency. Okay, there of course damping ratio is okay. It is we have calculated only for damping ratio 0. So okay, natural frequency you can determine, and then if you add the damping ratio, you can obtain the response for the system. Okay, so next is second order systems frequency response.